So my talk is based on these two papers written with Steen Hannested and Thomas Strum from Aarhus University in Denmark. And the first paper relates to Hubble tension and the second one relates to inflationary models. So the part one of the talk is related to Hubble tension, and so I'll just briefly introduce neutrinos. And we have active neutrinos have three mass eigenstates, which are quantum superposition of three flavored eigenstates, which are electron, muon, and tau neutrinos. And this sum of the neutrino masses is an important parameter in cosmology because the tightest bounds on sum of neutrino masses come from cosmology currently. And in cosmology, we use this approximation usually, where we consider all the masses to be same, which is not realistic, but it works well in cosmology. And then another important parameter is the radiation density of neutrinos, which we parameterize with this N effective parameter. And this contributes to the, so neutrinos contribute to the total radiation density in the early universe, and then later they become non-relativistic and contribute to the matter density. So the lambda CDM model parameterization is usually a 6-parameter scenario where we have this omega C and omega B as present day physical CDM and baryon densities. T times is a parameter related to the angular size of the sound horizon, which is the ratio between the sound horizon size and the angular diameter distance at photon decoupling. Tau is the optical depth to reionization, which measures the free electron number density at the line of sight. And NS and AS are the power loss spectral index and amplitude of the primordial scalar perturbations. And we consider this form of this primordial power spectrum. So what we consider is a model over and above lambda CDM, where we consider massive neutrinos and also the N effective parameter, and these neutrinos interact among each other with a interaction mediated by a heavy scalar where the mass is at least above the KeV range to allow for us to consider it an effective 4 fermion interaction limit. So CMB temperature is 0.26 eV. So if the mass is above the KeV range, then we can consider the phi particles to have decayed away, the mediator particles. So you can then consider it an effective 4 fermion interaction limit, and we can only concentrate on the neutrino self-interactions. So for this paper, we assumed a universal interaction model where this interaction matrix is basically diagonal. And then you can define effective self-coupling, G effective. And if G effective is greater than the Fermi constant, which is the weak interaction coupling strength. So neutrinos, after decoupling from the primordial plasma at 1 MeV, all the neutrinos will still be interacting with each other. So this self-interaction rate per particle can be defined as G effective square T nu to the power 5. And so neutrinos basically don't free stream until this gamma becomes, this interaction rate per particle becomes less than h, which is the Hubble expansion rate at that time. So basically, if you consider this kind of interaction where there's in the strong interaction range, where this G effective is actually 10 to the power 9 times that of G Fermi, then older data has shown that it can resolve the Hubble tension. So our cosmological model of interest is this 9-parameter model where we have this extra 3 parameters, N effective, sum of neutrino masses, and the log of G effective. And Christ et al. Has shown that this model can actually resolve the Hubble tension in the strong interaction regime when they only consider the CMB temperature data along with BAO and with similar goodness of fit to the data as lambda CDM. So in this model, N effective and H naught are positively correlated, and so there is a degeneracy between G effective and N effective, and this allows for high N effective values of around 4, and increasing N effective has the effect of increasing the expansion rate in the early universe, and that contributes to H naught, the value of H naught increases due to that. So, but Planck polarization data was not used for the main conclusions in this paper. So when the Planck 2018 likelihoods were released publicly, then we thought to test the model against the full likelihoods. And so the posterior for log G effective is actually bimodal, and it is divided in two parts, where one is the moderately interacting mode and another is the strongly interacting mode. And so what we did is first incorporate the full range of G effective and then separately run cases where we consider only the moderately interacting mode or strongly interacting mode. And also to compare with the non-interacting case where G effective is 0, we also take this NI new mode. So these are results with the full range runs. And since the posterior of G effective, as you can see here, is bimodal, this is the moderately interacting mode, and this is the strongly interacting mode. And so what we did is use a nested sampling algorithm instead of traditional MCMC. We used polychord along with CAM. And this model has a unique feature that it also splits the parameter space of theta, which is the strongest constraint parameter in the in any cosmological model usually. So this is a very unique feature of this model, that it completely separates the two modes of theta. And but in terms of Hubble tension, we are interested in this N effective parameter and the H naught parameter. And if you see the black curve, which is for the temperature and low L polarization data, where we don't use the high multipole data from polarization, then a large range of N effective is allowed, and so is a large range of H naught. So when you consider only the temperature data, then you can resolve the Hubble tension in this model. But as long as we include the high L polarization data, then the situation changes and N effective is very tightly constrained. And the reason is that polarization data is usually, the peaks in polarization data are usually more steep compared to the temperature data. And that's why they usually are more sensitive to the changes in the expansion rate close to recombination. And when you introduce strong self-interactions, then neutrinos can remain interacting even till the matter radiation equality. And so this data, the polarization data, usually is very sensitive to changes in N effective, even in this model. And we do not really see the N effective going beyond close to 3.5. And so the H naught value also remains bound to less than 70. So that is why when we include the polarization data, this model does not really solve the Hubble tension. So in these plots, we have treated the moderately and strongly interacting modes separately. The thing that is most important here is this NS parameter, where we can see that if you introduce strong interactions, then the preferred value of scalar spectral index actually decreases, and this will be important later when we discuss the inflationary models. This is to show that N effective and H naught are strongly correlated. So if you are not allowed to go to higher values of N effective, then you are not allowed to go to higher values of H naught either. So log G effective is degenerate with this theta MC and NS parameter, and this allows for a bimodal posterior distribution. And what we found in the strongly interacting case is that this model does not really allow H naught to go to very high values that can solve the Hubble tension. And even if we were to analyze with the fixed and effective value, then you can go up to like 69, 70, and still it won't provide a less than 3 sigma solution to the Hubble tension. For the non-interacting case, the situation is actually better than the strongly interacting case for the 3 neutrino interacting case, because this model actually disfavors the strongly interacting mode. So if we consider delta chi-square values or evidence ratio, we see that the strongly interacting mode is actually disfavored compared to the non-interacting case. But this is considering only 3 neutrino approximation. Now the issue is that neutrino self-interactions in all the 3 neutrinos is actually disfavored by particle physics experiments like tau decay or K-meson decay or double beta decay. So basically the only interaction that is allowed is among tau neutrinos currently. So but if you introduce the neutrino interactions only in one neutrino, the issue is that then the effect on the CMB power spectrum will be less, and then it will still not give you H0 values that you are looking for to solve the Hubble tension. So to conclude, with current data, this strong neutrino self-interaction model does not look like a promising solution to the Hubble tension. So the next part is related to the inflationary models. So I'll briefly introduce inflationary models where we have the scalar and tensor power spectrum, PS and PT. And then you can define this tensor to scalar ratio R, which is simply the ratio of the amplitudes. And then you can take a slow roll single field inflationary model Lagrangian, where V phi gives you these slow roll parameters, epsilon and eta. And then you can define these cosmological observables, NS and R, with respect to phi s, and which is the start of inflation. And inflation ends when these slow roll parameters become equal to 1. And in this case, we take epsilon to be equal to 1 for this. Then you can define this quantity number of E folds, where you start from phi s to phi e. And so for CMB observable fluctuations in CMB, you need this n star or number of E-fold links to be 40 to 60 before the end of inflation. So then if you are given a choice of V and n star, then you can predict the scalar spectral index NS and tensor to scalar ratio R defined at the start of the inflation phi s, where phi s is 40 to 60 E-fold links before the end of inflation. So here we consider two models, natural inflation and Coleman-Weinberg inflation. Both are actually disfavored more than 2 sigma in the lambda CDM plus R model, where we introduce this extra parameter because we are also considering tensor perturbations. And then our cosmological model of interest becomes this 10 parameter model. So previously we had 9 parameters. Now we have this tensor to scalar ratio as well. And okay, yeah, just 2 minutes. So we modify the neutrino-Boltzmann equation in both scalar and tensor perturbations for this, and we consider 2 scenarios where one is the 3 neutrino interacting and one is the 1 neutrino interacting scenario, because the 1 neutrino interacting scenario is more viable from particle physics point of view. And this is to show that how disfavored these models are. This magenta, the area covered by the magenta lines is the natural inflation prediction, and this Coleman-Weinberg prediction is the black curve, which has vanishingly small tensor to scalar ratio. So now, if you take the non-interacting model, then effect of n effective and sum of neutrino masses does expand the parameter space. But even if we consider the full data set where we have this Planck, Bicep-Keck, and the EXT data as well, where we use Planck lensing, BAO, RSD, and supernova data, then they are still disfavored at more than 2 sigma. But if you consider 3 neutrino interacting or 1 neutrino interacting scenario, then these models favor a lower NS value compared to the non-interacting case. And then you can accommodate both of these models, which are actually disfavored in the lambda CDM case. You can accommodate both in the 2 sigma range. So the neutrino self-interactions can keep these inflationary models afloat, even though they are disfavored in the lambda CDM model. Thank you.
So thank you, Shouvik. So we have We can have a couple of questions.
Okay. So you quoted the number 3.044. Can you change that number with these, if you have strong self-interactions?
Yeah, so if you have strong self-interactions in the all the three neutrinos, then they prefer slightly lower values of N effective.
Like the BBN?
Yeah, if you have self-interactions, then these 5 particles can decay into neutrinos, or they can decay into other particles, and based on that, N effective can change.
But even if I just had just the 3 neutrinos and just couldn't
You
that
just have the standard neutrinos, then changing N effective is difficult. So usually it is interpreted that if N effective is more than 3.044, there is some other massless radiation particle. So that is the interpretation usually. So standard model neutrinos are supposed to decouple at around 1 MeV, and that will give you 3.044 usually.
With that 0.044, I can't slightly tweak by having them have the energy getting shared during decoupling between the different flavors?
No, so this was done with the, I think this was a revised analysis where they considered all the flavor mixing and everything. So this was, I think, 3.044 plus minus, I think, 0.002 or something. Yeah, so it's very tightly constrained from, so this is a theoretical result, and this is tightly constrained from the theory perspective. But if you want more N effective, then you need to have species of radiation, which might be massless or low mass values. And if you need lower N effective, then you have to explain it with some interaction among neutrinos and
yeah, but what
something
I'm saying
like
is that 3.044 is a theory calculation that presumably had no interactions, right?
Yeah.
Okay.
So if there are no more questions, then let's thank the speaker.